A grand welcome to Outens Edu. For the previous lectures, we have done a detailed discussion about Laplace transform and its application. And we also discussed about region of convergence for both causal and anti-causal signals in detail and did so many problems. In this lecture, we are going to discuss about properties of Laplace transform briefly. And based on the properties of Laplace transform, we will do some problem. Okay. The first property is linearity. That means if x1t is Laplace transformable and whose Laplace transform is x1s and region of convergence is R1 and x2t the Laplace transform be x2x and region of convergence is R2, then we can apply the principle of superposition. That means Laplace transform of a into x1t plus b into x2t, where a and b are some constants. That is equal to a into x1x plus b into x2x. And region of convergence of this term is the intersection of ROCs of x1x and x2x. So region of convergence is R1 intersection R2. So this is the first property of Laplace transform. That is, superposition principle is applicable for Laplace transform. Okay. Next is time shifting property. Suppose Laplace transform of x of t is x of s and region of convergence is R. Then the delayed signal, that is x of t minus tau, is also Laplace transformable and whose region of convergence is same as that of x of x. And Laplace transform of this term, that is x of t minus tau, is equal to e raised to minus s tau into x of x. That is the time shifting properties of Laplace transform. Suppose, for example, this is our signal x of t. Then the delayed signal x of t minus tau. That means the signal is delayed by tau unit. That is, look like this. So instead of starting from 0, the signal will start from tau. That is a time delayed signal. Suppose in the case of a time advanced signal, that is represented by x of t plus tau. For example, x of t plus tau. This is an advanced signal. Suppose I am advancing this signal by tau unit. Then the signal will start from minus tau and the signal will look like exactly similar to the signal x of t, but there is a time advance. And the Laplace transform for this signal is e raised to s tau into x of x. Okay, and region of convergence for both signals are same, that is R. Now the third property is frequency shifting property or shifting in S domain. That means suppose x of t is Laplace transformable and whose Laplace transform is x of x and region of convergence is R. Then the frequency shifted signal, that is the x of t is multiplied by this term e raised to s0t, where s0 is a complex number. Then whose Laplace transform is equal to x of s minus s0. That means this signal is delayed by s0 or shifted by a unit s0. And whose ROC is this ROC of x of x plus real portion of s0. Suppose s0 is equal to 1 plus 2j. That is a complex number. Then the ROC of this signal is equal to r plus real portion of s0. That is equal to 1. Okay. Next is time scaling property. Suppose we have a signal x of t whose Laplace transform is x of x. Then the Laplace transform of this signal x of at is equal to 1 by mod a into x of s by a. And ROC is equal to r divided by a. That is a time scaling property. Okay. Next is time reversal property. If Laplace transform of x of t is x of x and region of convergence is R, then the time reversed signal, that is denoted by x of minus t. Then Laplace transform of x of minus t is equal to x of minus s. And ROC of the time reversed signal is minus of r. For example, we know that a unit step signal, this is 1 u of t. Okay. And the Laplace transform of u of t, that is equal to 1 by s. And region of convergence is sigma greater than 0. That is, real portion of s is greater than 0. Now, the time reversed signal, this is u of minus t. U of minus t. This is a time reverse signal or a folded signal. And the Laplace transform of this signal is equal to x of minus s. That is 1 divided by minus s. That is equal to minus 1 by s. And region of convergence is sigma less than 0. Okay. Next property is differentiation in time domain. Suppose Laplace transform of x of t is x of x and ROC is r. Then we want to find the Laplace transform of dx of t by dt. That means Laplace transform of dx by dt, that is equal to s into x of x minus x of 0 minus. That is the initial value of the signal x of t. ROC is same as that of r. Similarly, Laplace transform of the second derivative of x of t, that is d square x of t by dt square, that is equal to x square into x of x minus s into x of 0 minus, that is the initial value of x of t, minus x dot 0, where x dot 0 is equal to dx by dt at t is equal to 0, that is 0 minus. This is the value of x dot, that is the first derivative of x of t. And similarly, the Laplace transform of third derivative of x of t is equal to, this is x cube, third derivative, so the power of s is 3 into x of x. Now the power of x is decreased by 1. So minus x square into the initial value, that is x of 0 minus again the power of x is decreased by 1. So x into the first derivative of x of t whose initial value, that is at 0 minus, evaluating at 0 minus x double dot 0 minus. X double dot is the second derivative of x of t evaluating at t is equal to 0 minus. And for nth derivative, that is Laplace transform of nth derivative of x of t is equal to x raised to, this is nth derivative, so power of s is n, into x of x minus, then power of s is decreased by 1, s raised to n minus 1, x of 0 minus initial value, minus s raised to n minus 2 into x dot 0 minus. This continues, last term become x n minus 1th derivative of 0 minus. Okay, and for all this signal, the region of convergence is same as that of x of x, that is r. Next property is differentiation in s domain. Suppose Laplace transform of x of t is x of x. Then the Laplace transform of t into x of t, that is equal to minus 1 raised to 1 into first derivative of x of x, that is dx of x with respect to s, that is dx of x by ds. And region of convergence is same as that of r. Now Laplace transform of t square into x of t, that is equal to minus 1. Now the square of t, so minus 1 square into d square x of x by, so this become d square, minus 1 square means 1, d square x of x by, for this minus 1 raised to 1, so that become minus d x of x by dx. Now Laplace transform of t raised to 3 x of t, that is equal to minus 1 raised to 3 third derivative of x of x with respect to x. So this is equal to minus d cube x of s divided by ds cube. And ROC is same. And in general, we can write Laplace transform of t raised to k into x of t is equal to minus 1 raised to k, the kth derivative of x of x. Next property is integration in time domain. Suppose Laplace transform x of t is x of x. Then Laplace transform of integral minus infinity to t x of tau d tau. This is the first integration. That is equal to x of x divided by s plus 1 by s into integral minus infinity to 0 minus x of t dt. That is the value of this integral from minus infinity to 0 minus divided by s plus this term, that is x of x divided by s. Next property is time convolution. If x1t and x2t are both are Laplace transformable, that is x1t Laplace transform is x1s and ROC is R1, and x2t is also Laplace transformable whose Laplace transform is s2s and ROC is R2. Then x1t convolution of x2t. We want to find the Laplace transform of x1t convolution x2t, that is equal to x1s into s2s. That is multiplication of these two signals x1x and s2s. That is convolution in time domain is equal to multiplication in Laplace domain, and whose ROC of this signal is R1 intersection R2. That is intersection of ROCs of x1x and x2s. Okay. This property can be used to find the output of a system. Suppose we have a system. This is our system, and h of t is the impulse response of the system. And for any input x of t, let y of t be the output. So by using the property of a linear system, the output y of t for any input x of t is equal to x of t convolution of h of t, where h of t is the impulse response of the system. Now, taking the Laplace transform, we get y of s is equal to x of x into h of s, or this implies h of s is equal to y of s divided by x of x. This is the h of s is the Laplace transform of impulse response. This is nothing but the transfer function of the system. So transfer function of the system is equal to Laplace transform of output to that of the input by assuming all initial conditions 0. That is same as that of the impulse response of the system. Next property is frequency integration. If Laplace transform of x of t is x of x, then we have a signal x of t divided by t. Then Laplace transform of this signal, that is x of t by t, is equal to integral of x of p. This is x of x, we are replacing x by p with respect to dp. The limit of integration is from s to infinity. This is called frequency integration. Next property is frequency convolution. If we have two signals x1t and x2t, both are Laplace transformable, then Laplace transform of x1t into x2t, that is a product of x1t and x2t, that is equal to 1 by 2 pi j into x1x convolution of x2x. The Laplace transform of product in time domain, that is x1t into x2t, that is equal to the convolution in s domain, that is 1 by 2 pi j into x1s convolution of x2x, that is the frequency convolution. Now initial value theorem. Suppose we have signal x of t whose Laplace transform is x of x. Now we want to find the initial value of the signal x of t, that is x of 0 plus is equal to limit s tends to infinity s into x of x. So using initial value theorem, we can find the initial value of this signal x of t without finding the inverse Laplace transform. If we know x of x, we can directly find x of 0 plus by applying this limit s tends to infinity s into x of x. This is a very important theorem and usually very, very useful. Next is final value theorem. Final value theorem is used for finding the steady state value of a signal. Steady state signal value of a signal means the value of signal when t tends to infinity. Final value of the signal x of t means limit t tends to infinity x of t. This is equal to limit s tends to 0 s into x of x. So the steady state value of the signal, that is x of infinity, that is equal to limit s tends to 0 s into x of s. This is the theorem used to find the final value of a signal. Next is conjugation property. If we have a signal x of t whose Laplace transform is x of x, then the conjugate of x of t, that is x conjugate t, whose Laplace transform is equal to x conjugate of x, this also conjugates. Okay. If x of t is a real valued signal, that means x of t is real valued signal, then x of t is equal to x conjugate t. In this case, x of s is same as that of x conjugate of x conjugate. This both will be same in the case of a real valued signal and ROC is always same. Right. This is inverse Laplace transform. If x of t whose Laplace transform is x of x, then by taking the inverse Laplace transform, we will get x of t. That means x of t Laplace transform will give x of x and inverse Laplace transform of x of x will give x of t. X of t is equal to L inverse of x of x, and this can be evaluated by using this integral, that is equal to 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity x of s e raised to st, here s is plus in respect to ds. This is a formula for evaluating the inverse Laplace transform. Sigma will depending on the ROC of x. Suppose ROC of x of x is like sigma 1 less than real of s less than sigma 2. This is the ROC of x of s. Then sigma will be chosen in such a way that sigma 1 less than sigma 2. This is the condition on sigma. Based on the properties of Laplace transform, we have to do some problem. Our first problem is x of t is equal to e raised to minus 3t u of t plus e raised to minus t cos 2t u of t. So this is a causal signal. We know that any signal multiplied by u of t will make the signal as a causal. And the Laplace transform of this portion is 1 divided by s plus 3. And region of convergence is real portion of s, that is sigma greater than minus 3. Region of convergence of the signal that we can draw as this is minus 3. This is our s plane sigma j omega. Okay. Now this portion is the region of convergence. Now here we can use a property. We know that if Laplace transform of x of t is equal to x of x, then Laplace transform of e raised to minus at into x of t, that is equal to x of s plus a. Okay. Now we can take cos 2t. Now Laplace transform of cos 2t, that is equal to s divided by s square plus 2 square, that is 4. Now Laplace transform of e raised to minus t cos 2t. By using this property, this is equal to s plus 1 divided by s plus 1 the whole square plus 4. Okay, that is equal to s plus 1 divided by s square plus 2s plus 5. So, what is the ROC of this term? For finding the ROC, consider this denominator polynomial, that is s square plus 2s plus 5. We can factorize. What is the value of s? S is equal to minus 2 plus or minus root of 4 minus 4ac, that is 20 divided by 2. That is equal to minus 2 plus or minus, this is root of minus 60, that is j into 4 divided by 2. That is equal to minus 1 plus or minus j2. So real portion of the signal, this s is minus 1. So ROC of this signal is real of s, that is real of s, that is equal to minus 1. So s sigma is greater than minus 1 is the ROC of the signal, that we can draw as this is minus 1. This is the region of convergence. This is our explained j omega sigma. So the ROC, this is a linear combination of two causal signals. So ROC is the intersection of both this ROC of this portion in intersection with ROC of this signal. So ROC of this is minus 3 and this is minus 1. So ROC of the combined signal is intersection, that is minus 1. This is minus 1. So this portion of the S plane. So ROC is sigma greater than minus 1. This is the ROC of this signal x of t. That is the intersection of this portion and this portion. I think it is clear. Now our question is, we have given x1s, that is equal to 1 by s plus 2, and s2s is given 1 by s plus 2 into s plus 3. Now we want to find the region of convergence of the signal x1 of s minus s2s. Okay. Now what is the ROC of this signal? ROC of the signal is sigma greater than minus 2. That is real portion of s greater than minus 2. That we can draw as this is minus 2 or s plane j omega sigma. So this is the region of convergence of S1s. Now for S2s we have two poles. One pole is at s is equal to minus 2 and other pole is at s is equal to minus 3. So in S plane I am marking the poles. This is minus 2, minus 3. This is j omega axis sigma S plane. So we know that ROC will never contain any pole. So ROC of the signal is sigma greater than minus 2. This is the ROC of the signal. That is sigma greater than minus 2. That is ROC will not contain any poles. Now what is, so that means the ROC of both the signals are sigma greater than minus 2. Now we want to find the ROC of the signal S1s minus S2s. Now let us check what is S1s minus S2s. S1s minus S2s, that is equal to 1 divided by s plus 2 minus 1 divided by s plus 2 into s plus 3. Now taking the LCM, this becomes s plus 3 minus 1 divided by s plus 2 into s plus 3. So here s plus 3 minus 1, that becomes x plus 2. So this is equal to s plus 2 divided by s plus 2 into s plus 3. We have 0 at s is equal to minus 2 and a pole is also at s is equal to minus 2. So here a pole 0 cancellation taking place and the difference S1s minus S2s, that is equal to 1 divided by s plus 3. So the ROC of this signal is real portion of S is greater than minus 3. That means sigma greater than minus 3. So ROC is equal to sigma greater than minus 3. Okay. So this is our minus 3. So ROC of the signal is this portion greater than minus 3. That happens because of pole zero cancellation. Now our question is x of x is given. We want to find x of t. That is, we want to find the inverse Laplace transform. Now look at this ratio. That is 2s square plus 5 divided by s square plus 3s plus 2. That means degree of numerator and denominator are same. That is equal to 2. So we want to make it into proper fraction. That means degree of numerator should be less than that of the degree of denominator. That can be achieved by making use of long division. So I am going to divide numerator by denominator. I am going to divide 2s square plus 5 divided by s square plus 3s plus 2. So first I write 2 here. Now 2 into s square, that is 2s square, 2 into 3s, so 6s, plus 2 into 2, that becomes 4. Now subtract, this becomes 0 minus 6s plus 1. Okay, so I can write this fraction as 2s square plus 5 divided by s square plus 3s plus 2, that is equal to 2 plus minus 6x plus 1 divided by s square plus 3s plus 2. Okay. Now I am going to write 2 plus minus 6x plus 1. And I am going to factorize the denominator term here. This I can write this as s plus 1 into s plus 2. Okay. Now using the partial fraction method, this can be written as 2 plus a divided by s plus 1 plus b divided by s plus 2. Now find the value of a and b. Take the inverse Laplace transform of this portion. What is a? A is equal to, we can use the method of residue. That is, a is equal to, we have pole at s is equal to minus 1. So s plus 1 into this function, this entire function, and evaluating at s is equal to minus 1. That is, this into minus 6s plus 1 divided by s plus 1 into s plus 2. This is evaluating at s is equal to minus 1. This s plus 1 and s plus 1 will cancel and put s is equal to minus 1 in the remaining terms. So this is equal to minus 6 into, for s, minus 1 plus 1 divided by s is equal to minus 1 plus 2. That is equal to minus 1, minus 6 into minus 1. That is 6 plus 1 divided by 1. That is equal to 7. That is a. So the value of a is 7. Now we want to find the value of b. B is equal to the pole at s is equal to minus 2. So s plus 2 into this entire portion, that is minus 6s plus 1 divided by s plus 1 into s plus 2. This is evaluating at s is equal to minus 2. Here s plus 2 and s plus 2 get cancelled and put s is equal to minus 2 in the remaining terms. So this is equal to minus 6 into minus 2 plus 1 divided by minus 2 plus 1. So this is equal to minus 6 into minus 2, that is 12 plus 1 divided by minus 2 plus 1, that is minus 1. So that is equal to minus 13. So a is equal to 7 and b is equal to minus 13. We can write s of x is equal to 2 plus a is 7 divided by s plus 1 and b is minus 13. That is minus 13 divided by s plus 2. Now take the inverse Laplace transform. This implies x of t is equal to, the inverse Laplace transform of 2 is 2 times del of t plus 7 into e raised to minus t u of t minus 13 into e raised to minus 2t into u of t. So this is the inverse Laplace transform of the signet. Now our question is x of x is given. We want to find x of t. That means we want to find the inverse Laplace transform. Here x of x is x of s plus 2 plus 4 times e raised to minus 3s. Okay. So by divide by s plus 1 into s plus 3. So I can write this as s plus 2 plus 4 into e raised to minus 3s divided by s plus 1 into s plus 3. Now I am going to split these terms as s plus 2 divided by s plus 1 into s plus 3 plus 4 times e raised to minus 3s divided by s plus 1 into s plus 3. Okay, now let this is equal to, let the entire term be x1s plus this term 4 divided by x plus 2 into s plus 3, let this be s2s into e raised to minus 3s. So I can write s of x in like this. Okay. Now I am first evaluating x1s. That is x1s is equal to s plus 2 divided by s plus 1 into s plus 3. By using partial fraction expansion, I can write this as a divided by s plus 1 plus b divided by s plus 3, where a is equal to s plus 1, that is a pole at s is equal to minus 1. This into this entire term, that is s plus 2 divided by s plus 1 into s plus 2, s plus 3. This s plus 1 and s plus 1 cancel. So this is evaluating at s is equal to minus 1. So by substituting the value of s, we get minus 1 plus 2 divided by minus 1 plus 3. That is equal to 1 by 2. The value of b is equal to s plus 3 into this entire term, that is s plus 2 divided by s plus 1 into s plus 3. This is evaluating at s is equal to minus 3. This term gets cancelled. So substituting for s is equal to minus 3. Minus 3 plus 2 divided by minus 3 plus 1. That is equal to minus 1 divided by minus 2 is equal to 1 by 2. That means a is equal to 1 by 2 and b is equal to 1 by 2. So we can write this is equal to 1 by 2 into 1 by s plus 1 plus 1 by 2 into 1 by s plus 3. Now taking the inverse Laplace transform, this implies s1t, that is equal to 1 by 2 into e raised to minus t u of t plus 1 by 2 into e raised to minus 3t u of t. Okay. So we find the inverse Laplace transform of this portion. Now we want to find the inverse Laplace transform of S2S. That means S2S is equal to this term, that is 4 divided by S plus 1 into S plus 3. By using partial fraction expansion, we can write this is equal to A by S plus 1 plus B divided by S plus 3. Now evaluate the value of A and B. A is equal to S plus 1 into this entire term, that is 4 divided by S plus 1 into S plus 3. This is evaluating at S is equal to minus 1. This gets cancelled. So this is equal to 4 divided by minus 1 plus 3. That is equal to 4 divided by 2. That is equal to 2. So the value of A here is 2. Now B is evaluating as B is equal to S plus 3 into 4 divided by S plus 1 into S plus 3. S plus 1 into S plus 3. Evaluating at S is equal to minus 3. This is cancelled. So this becomes 4 divided by minus 3 plus 1. That is equal to 4 divided by minus 2. That is equal to minus 2. So we can write S2x, that is equal to A means A is equal to 2. That is 2 s plus 1 minus 2 divided by s plus 3. Now take the inverse Laplace transform. We get s2t is equal to 2 into e raised to minus t u of t minus 2 into e raised to minus 3t u of t. Okay, so we find x1t and x2t. Now we have a term e raised to minus 3, that is the exponent term in s2s. So by using the property, we can write s2s into e raised, the inverse of s2s into e raised to minus 3s as 2 into e raised to minus t minus 3 minus 2 into e raised to minus 3 t minus 3, a delay of 3. This whole into a delay is given to u of t, that is u of t minus 3 plus x1t, or x1t is this term, that is 1 by 2 into e raised to minus t u of t plus 1 by 2 into e raised to minus 3t u of t. So this is our answer. Right. So in this problem, we first evaluate the Laplace inverse Laplace transform of this term, and due to this exponential term e raised to minus 3s, we given a delay in the time response, that is a delay by 3 units, that is t is replaced by t minus 3. The same delay is given also to unit step signal. So we have signal, we want to find the Laplace transform of this signal. This is a triangular signal. Okay, now look at this figure. The value of the signal is increased linearly from 0 to 3. From at time t equal to 3, this again linearly decreasing to 0 and reaching at time t equal to 0. So I am going to do this by making use of a properties of Laplace transform. We know that Laplace transform of dx by dt is equal to s into x of s, and I am assuming initial conditions 0. Now first I am going to differentiate the signal. So this is a point, both x is equal to 3 and y is equal to 3. This is the origin and the point 0, 0. This is the point x is equal to 6 and y is equal to 0. So differentiation means finding the slope, that is y difference by x difference. Now I am going to differentiate. Now this is our time axis 3, this is 6, this is 0, and dx by dt. But the slope of this line, that is y difference. So our point is 0, 0 and 3, 3. So the dv by dx of this line is y difference by x difference, that is 3 minus 0 divided by 3 minus 0, that is equal to 1. So up to this, the signal become 1, the value is equal to 1. Okay, now from what is the derivative of this line? That is, we have point 3, 3 and this point is 6, 0. So slope is equal to 0 minus 3 divided by 6 minus 3, that is equal to minus 3 divided by 6 minus 3, that is 3, that is equal to minus 1. So this will look like this. So the value of the signal is minus 1. Okay. Now I am going to differentiate the signal again. So we can write this is equal to d square x by dt square. During this portion of the signal, it is a constant. So value of the derivative of a constant is equal to 0. During this portion also, this is a constant. So slope or derivative is equal to 0. Now we want to find the slope at this point at 0 minus to 0 plus, 3 minus to 3 plus during this point and during this point. That will result in an impulse. So from here 0 minus to 0 plus, the peak value is 1, this is 0. So the derivative of this become an impulse of strength 1. During this time is equal to 3. During this point to this point, the derivative is 0. During at this instant, jump from 1 to minus 1. This point is minus 1, 1. So the derivative of this line is minus 1 minus of minus 1. That is equal to minus 2. So at this point, we get an impulse of strength minus 2. And again from this to this point, that is a constant. So derivative is equal to 0. During this period, that is 6 minus 2, 6 minus 2, 6 plus. This is 0, 1. So 0 minus of minus 1, that is equal to 1. So we get a impulse of strength 1 at t is equal to 6. So this is the d square x by dt square. Now take the Laplace transform of this signal. This is an impulse. So the Laplace transform impulse signal. So we can write this as d square x by dt square. That means d square x by dt square. That is an impulse of strength 1. That is del of t. This is a delayed impulse of strength minus 2. That is minus of 2 del of t minus 2. And this is an impulse of strength 1 delayed by 6 unit. So plus del of t minus 6. So this is d square x by dt square. Now take the Laplace transform of d square x by dt square. So that is equal to s square into x of x. That is equal to the Laplace transform of del of t is 1. Minus 2. This is a delayed impulse. The Laplace transform is e raised to minus 2 s. Plus this is delayed by 6 units. That is e raised to minus 6s. Okay. Now x of x is equal to, this is taking to the RHS, 1 by s square into 1 minus 2 e raised to minus 2s plus e raised to minus 6x. This is the Laplace transform of this signal. The next session we will discuss about the analysis of linear time continuous systems. Then causality of system, stability of the system, invertibility of the system, and based on that we will do some problems. Okay, thank you, bye.